going to see an overall increase in the number of storms. It could even be a decrease in the number of storms.
Could be.
But the number of Cat 4 and 5 storms will increase.
Kevin, Sam, are you ready? Go ahead.
Okay. Can you hear me?
Yes.
Okay. Can you see my shared screen?
Yes.
Yes.
Okay. Excellent. Good morning, good afternoon, and good evening. Welcome to the Source to Sink webinar series. This webinar is co-sponsored by National Science Foundation, NC State, LSU, East China Normal University, CSK Lab, as well as UTRACH. So today it's my great honor to introduce Dr. Sam Bentley, and he will give a talk about submarine landslide and morphodynamics of Mississippi River Delta front. So before we start this seminar, I just want to remind everyone, on YouTube, we actually have an active channel to archive all the past Source to Sink talks, and they are open and they are free to the public. We also have a Twitter channel, which is called Source to Sink. On this Twitter account, we post all different kinds of tweets regarding the seminar announcement. And you can actually, if you use Twitter, you can actually receive information about Source to Sink webinar. A quick reminder about the seminar next week. On Wednesday, September 22nd, there will be a talk about groundwater discharge, and the talk will be given by Dr. Elko Lujendik. And this is a very interesting topic because it links the water and material exchange between the land and the ocean. It's a relatively understudied area. So a very brief introduction about Dr. Sam Bentley. So over the past 9 years, I have been working with Sam on many different projects. Sam is right now the Vice President of Office of Research and Economic Development. He's also the Professor and Harrison Chair in Sedimentary Geology in the Department of Geology and Geophysics. Sam received a PhD from Stony Brook back in 1998. And he has been spending over many years, he has been studying the Mississippi system, including the Mississippi Delta. So a while back, Sam gave a talk about the entire Source to Sink system of the Mississippi, from the upper Mississippi basin all the way to the Delta, and then to the northern Gulf of Mexico. And today his topic will be focused on the Delta front. Sam, I'm going to stop sharing.
Great, thank you, Kevin. So I'm gonna bring mine up. Okay, Paul, can you enable screen sharing, or Kevin or someone? I'm getting a screen sharing disabled error.
I'm sorry, now you should be able to.
Okay, good. Ah, yes, there we go. Okay, everyone, it's a great pleasure to be here with you today, and I think what Paul has done over the last year and more is just amazing to unite our community around the world. So I wish you good morning, good afternoon, and good evening to all, like Kevin did. Quick introduction. Like many of us who work at universities that are on some of the great rivers and river deltas of the world, there's a long history of geoscience in general and coastal geoscience research specifically at LSU. And I'm kind of a fan of the history of science, and so I'm just going to go quickly through some of the notable events at LSU over the last more than a century. So in the top right-hand figure, you can see that this is the first geologic map that was ever published to the state of Louisiana. It was published as a result of a geologic survey called the Louisiana Geologic Survey in 1870, and the work was all done by horseback. In 1922, the LSU Geology Department was founded. In 1936, the first, if anybody wants to write to me and offer some corrections to this, but I think one of the first major publications on a major river delta was Louisiana Geological Survey bulletin number 8, shown here in the lower portion of the right-hand side. Many of us are familiar with the Harold Fisk's maps of the meander belts. Those were published in 1944. 1954, the Coastal Studies Institute was founded to study global geological and physical processes coastally. Department of Oceanography was founded in 1970. CSI was then expanded in 2012. And in the last decade or so, LSU is consistently ranked as one of the top coastal research universities in terms of coastal oceanographic funding, identified by the National Science Foundation. And we also are home to the College of the Coast and Environment, where Kevin holds tenure, is home to 4 of the 10 most highly cited wetland scientists in the world. So there's a lot of great stuff going on, and we welcome everybody to come visit us, particularly once the Delta variant surge subsides. So now let's get to the meat of the talk. What I want to first of all say is, yeah, certainly I'm giving this talk, but Kevin and Jillian Maloney and Ioannis Georgiou and Mike Miner and Jeff Obelts and Jason Chater and all of our students have contributed hugely to this over the last 8 years at this point. And the figure in the center shows the location of the Bird's Foot Delta that many of you are familiar with. It's geographically located in the north central portion of the Gulf of Mexico, as shown here in this yellow box. And this area sort of highlighted offshore of the Bird's Foot is what we call the Mississippi River Delta front. Now, this is a very active area in terms of oil production, oil transport, and you can see that in this figure. Again, the Mississippi Delta front, which is essentially the sediment apron from about 10 meters to about 200 meters water depth, is covered up by pipelines, which are shown here in gold, and by wells and well platforms for oil and gas production. So geohazards associated with the Delta front are terribly important. So we're going to look at the motivation and aims for the talk, talk about some synthesis and data analysis studies, pilot studies that we conducted over the last several years, and some concepts for future work. So just like I just mentioned, the Delta front is an area for active production and transfer for oil and gas, and it's impacted by submarine landslides at a range of spatial and temporal scales. Mostly we've understood these through the impacts of hurricanes that drive these major landslides on the Delta. The last regional survey, sort of regional synoptic survey, was undertaken in the late 1970s by Jim Coleman of the Coastal Studies Institute at CSI at LSU. And so there's a really big need to understand from a risk and hazard assessment perspective what's going on the Delta front. So we're going to look, so the project that Kevin and I had been funded on, which ended in about 2018, and we'd like to start up again when we have the opportunity. We're going to look at some of the results from data synthesis, some geophysical data analysis, 2 pilot studies that we conducted, and some topics we'd like to look at for future. So you guys aren't going to be able to get this right now, but if you come back to the recording that Paul will put up in a few days, these are the key references that this talk is based on. And they include several invited papers for Earth Science Reviews, Marine Geology, and the Geological Society of London, as well as contributed papers to Geology, Geomarine Letters, and Marine Geology. So this is a block diagram that combines actual bathymetric data and sort of depositional or facies analysis with some interpretive subsurface features. So the Delta front is characterized by gullies that cut across the sloping Delta front, and mud flows down through these gullies, and then the mud flows and coalesces to form lobes of sediment out on the lower portions of the Delta front. And this is characterized in the subsurface by remolded clays that are shaped by self-weight consolidation, and lies on a basement of Pleistocene silts and clays. A lot of rapid sediment accumulation, waves, and other features, other events trigger mud flows, and these are all in some ways linked to the processes on the subaerial delta, particularly sediment delivery. So the basic question that I want to explore for this presentation is the following. We know that the Mississippi Delta Front is a region of active sedimentation and landslides. We know that major hurricanes cause landslides, but the submarine landslides occur under what conditions and over what spatial and temporal scales, and what processes drive these. So like I said, the last major survey was done 40 years ago. And in 2013, the U.S. Bureau of Ocean Energy Management asked our research team to collect data that had been gathered historically, to conduct a couple of pilot studies, and over the course of several years, make some recommendations on next steps. So that's what we're going to look at today. This is a regional snapshot of oil and gas wells and platforms in the northern Gulf of Mexico. We're going to zoom in the next slide to show you some more of the characteristics. So this is from a paper by Jason Chater, who is part of our research team. He's from the USGS. You can see here platforms shown in red on the right-hand side. You can see the Bird's Foot Delta. Pipelines are shown in yellow. And the Delta front is sort of encompassed by this dashed line that you can see right here. And on the left-hand panel, these are the tracks of hurricanes that have gone across the study area in pretty much the last 40 or 50 years. So within the time frame of oil and gas exploration. So this is an area that receives a lot of sediment, and it gets impacted by a lot of hurricanes, including, we're in our second one for the season today that's coming up across the Louisiana coast. An example of this, of how this impacts the Delta, is with Hurricane Ivan, which was, I think it reached Category 5, or at least Category 4 status out in the Gulf of Mexico in 2004. And waves from Hurricane Ivan toppled a major oil and gas platform that was in about 100 meters water depth. There were 16 oil wells that were severed and were flowing freely into the ocean. The total cost of restoration, which is not yet complete, 17 years later, was over $1 billion for one platform. And there's oil still leaking from some of those oil wells, and lots of other pipelines were damaged as a result. We were actually able to survey with Jason Chater's group, survey over this location in 2017. And this is a multi-beam map showing the failure scarp here, the location of the platform that was toppled, again highlighted in the multi-beam data. There are frontal scarps farther down from mud flows, and pressure ridges that are farther down slope. So this is really a big deal. If you think about it, more than $1 billion risk for each one of those platforms that's out there, it's a major problem. This is a seismic profile, multi-channel seismic profile across, and this is this right here. This is the location of the platform, and you can see this slab right here going from left to right is the mud flow that actually toppled the platform itself. It was a slab on the order of 20 to 30 meters thick that slid down slope. So what do we need to sort of understand from a mechanical perspective? Well, many of us know the basics here. Basically, a slab sitting on a slope has got an immersed weight. The downslope force is a function of the weight and the angle of the slope, which is and the weight is a function of the thickness and the density. Delta P is the wave generated cyclic pressure difference. So as a wave goes by and the trough and the crest goes by, it produces a variation in the pressure on the seabed that, particularly if there's free gas in the seabed, can create instabilities. Waves and currents also produce shear stresses on the sediment surface, and these can drive sort of thinner flows And all of these factors contribute to various types of instabilities on slopes like this. This is a simple mechanical model. It's still used for looking at the mechanics of flows. It's an analytical solution that's quite amenable to classroom use, for example. And it shows sort of the spatial distribution of delta P pressure forces as a wave crest goes by, and it produces a load on the seabed. And as the trough goes by, it produces an unloading of the pressure on the seabed. And at one point in time, the force actually creates a sort of an arcuate force that can produce something that might look like a slump or a slide or a full-scale mud flow going down slope. So for the synthesis portion of the study, we looked at well over 100 data sets and many articles and reports, and we integrated the data sets using ArcGIS and Kingdom Suite to develop projects. Jillian Maloney did a lot of this for the project. We also conducted 2 pilot surveys in 2014 and 2017 using geophysics, various geophysical tools, coring tools, approaches to dating sediments using radioisotopes, geological and geophysical properties, and there's some geotechnical work right now that's ongoing with our colleague in the College of Engineering here at LSU. So we did a lot of work on synthesis. I'm going to focus on the timing and focus of historical studies and a historic shift in delta progradation patterns that we've observed in just in the last decade. And the publications that are the basis for this are Jillian Maloney et al., 2018 and 2020. These are the kind of data sets that we used. We were able to obtain multi-beam and digital sub-bottom data sets from various industry partners, very high quality and very much amenable to time series analysis of seabed morphology. This is a time series plot of sort of areas, topics of interest studying the Mississippi Delta front, beginning in the 1950s and early 60s when offshore oil production was in its infancy. Of course, in the 1960s, we had 2 massive hurricanes in the Gulf of Mexico that really caught everyone's interest. And this was Betsy and Camille. And people went through, scientists and engineers went through a period of looking at the impacts of gases, wave triggering, and geotechnical properties on seabed instabilities. The most recent bathymetric study was done here in the late 1970s. Multi-beam technology advanced significantly in the 1990s through the present day. And then there have been continued hurricanes, some major noteworthy historic hurricanes over the last 20 years or so, shown right here. This is actually a time series of publications that have come out by topic. And the tall red bars here show the names and the years of major hurricanes or hurricanes that went across the Delta. Lily was a minor one. And clearly you can see that there's basically a burst of publication energy following each of these periods of hurricanes, and then things die off. And so as a result, we know a fair amount about the genesis of instabilities by hurricanes, but not much about anything else. So the next major point I want to touch on is the change in historic progradation patterns of the Mississippi River Birdsfoot Delta, particularly the subaqueous delta. We're calling it here the Mississippi River Delta front. If you're looking at it in terms of a clinothem, this would be the forceps of the subaqueous clinothem. Historically, these outlets of the Mississippi Delta, and even prehistorically, have been prograding at rates around 75 meters per year, naturally, have been prograding at these rates with vertical accretion rates or rates of up to about a meter per year. So while, during the mid-20th century and early part of the 20th century, human engineering on the Mississippi River reduced the sediment load by a factor of about 50%. And this is from a paper, this is originated from Mead and Moody, and we redrafted the figure in 2016 for a review paper. So one interesting question is, we know that many of us are familiar with the story that this sediment reduction has caused a huge impact in terms of terrestrial land loss, wetland land loss, and coastal erosion. But what about in the subaqueous portions of the Delta? So we're going to look at data sets that Jillian collected following the work of Coleman and others for Southwest Pass, South Pass, and Pass Elutra. So what I'm going to show you is a time series of the location of the 10-meter isobath from historical data sets that we and others have collected over the years. So we're starting out in 1764, and the green is the distribution of the modern subaerial delta. So here's the 10-meter isobath in 1764, 1838, 50 meters per year, 1874, 60 meters per year, 1906, almost 100 meters per year, 1940, 70 meters per year. And it's at this time that the dam construction reached its peak in the Mississippi River Basin. And then the progradation rate declined further. And now portions, as you can see, this pink line, there's some retreat taking place. If we look at the other outlets of the river, there is already from 1979 to 2008 for South Pass, there is transgression taking place at the rate of about 20 meters per year. And at Pass Elutra, we're also getting almost 30 meters per year of regression. So this shows the time series over different time slices for Southwest Pass, South Pass, and Pass Elutra. So there's a demonstrable impact from terrestrial sediment load carried by the Mississippi, and that's now being felt in the subaqueous delta. What about deeper? Well, if we look at Southwest Pass, South Pass, and Pass Elutra at deeper isobaths, what we find overall, without going into the details, is that Southwest Pass and South Pass are still prograding at depth, out around 70 to 80 meters depth. But Pass Elutra is transgressing, this one down here, is presently transgressing at all depths. And in some of the shallowest locations, Southwest Pass and South Pass are also transgressing. So there's sort of a phase lag for deep water morphodynamics with respect to terrestrial sediment supply. And this is the bathymetry, some of the difference of depth maps that Jillian created for this project. So this main story here is it's very heterogeneous, but there are some demonstrable trends. So we conducted some pilot studies in 2014 and 2017. And the focus, because it's a vast area, it's 2,000 square kilometers, we looked at hot spots where we had time series data sets off of the main Mississippi River passes so that we could do some change detection and radioisotope geochronology that was coupled with good geophysical morphological understanding. So we conducted sort of a small boat study in 2014, published papers in Geology and Geomarine Letters, and 2017 collaborated with USGS for work off of the RB Point Sur. And the analyses are ongoing right now for work. We have a couple of master's theses that have been published, a master's thesis and a dissertation that's ongoing. And the papers from those will start coming out pretty soon, we think. So now we'll look at some examples. The first study that we're going to take a quick look at is a paper led by Jeff Obelts, published in 2017, part of his dissertation, where we did a time series analysis of bathymetric change from 2005, 2009 to 2014. And importantly, this is a period of when there were no hurricane strikes on the Mississippi River Delta. So anything that we see is a result of something else besides a hurricane that's driving sediment dynamics. This is an example of a difference of depth map that covers part of the area where where warm colors are deepening and cool colors are shoaling. The bottom line is the major observation is the following. First of all, the gullies that we've identified are growing deeper by about 1 meter per year. And the sediment lobes fed by the gullies are growing shallower by about 1 meter per year. The gully and lobe width during these times doesn't change. And the bathymetric changes that we're observing over the course of about a 10-year period exceed the sediment deposition rate substantially. So this is actually a change in base level. And so these changes are being observed caused by without forcing from large hurricanes. So one of the questions we were wondering about was, okay, so we don't have major hurricanes. We also, several of the folks in the party on the project knew something about wave mechanics. And so we wondered, well, are we using the right wave models to predict the delta P at the seabed? And so Ioannis and Kevin and others on the project decided to use a more complex model to look at pressure differentials created on the seabed by nonlinear waves to see if the pressure difference under nonlinear wave theory was different from linear wave theory and might be enough to actually drive seabed motion. So the question is, can nonlinear waves create a different delta P result that could drive seabed motion? And the answer is yes, they can. So the top plot shows the wave height for the solid line is a hurricane, a hurricane wave with wave height predicted by model development. And the corresponding solid line on the bottom plot shows the delta P variation at different water depths. The dashed line is something that is a wave that you would expect from a typical winter storm, maybe a strong winter storm, but still a winter storm, an annual event with a delta P predicted by nonlinear wave theory. And what you can see is that a relatively weak storm can, if you use a different wave model, can produce a delta P that's substantially higher than that's predicted by linear wave theory. Now, this is important for a number of reasons. The most important one that I can think of is that there's been a lot of hazard work done on the Mississippi River Delta, looking at wave mechanics and the fact and how it drives seabed instabilities. And what this means is that all the previous studies that are mostly based on linear wave theory are wrong. They underestimate the hazard because they underestimate the capability of storm waves to produce pressure differentials that can drive seabed motion. So as a part of the pilot study, we also did a fair amount of radiochemical work dating sediment cores collected in the bathymetric grid off of Southwest Pass. And what we found is, as what you would expect, rapid sedimentation on the order of millimeters per day based on beryllium beryllium geochronology, beryllium-7 geochronology, centimeters, decimeters per year from lead-210 geochronology. And these line up pretty well with rates of seafloor change estimated from bathymetric change, such as we, for the areas where the lobes, where the seabed is not subsiding so much. Like, for example, the ridges between the gullies, most of the seabed change is driven by sediment accretion. My students, Jeff Duxbury and Nathan Figueiredo, are working on the more radiochemical work in these regards right now. Another one of my favorite results to come out of the study is an inspiration from Jeff Obelts, who is Kevin's PhD student. And he produced a map that I hope he copyrights the term. It's an anti-gasopac map. There's a tremendous amount of gas in these sediments. So you get blanking of sub-bottom sonar signals very quickly. And so the blanking depth, or the wipeout depth, is basically an indicator of gas distribution in the seabed. And so this is a color contoured map of the wipeout depth in sub-bottom data that shows that for most of the seabed throughout the study area, we're only getting 0 to 1 meter or so penetration for data recovery for high frequency sub-bottom data. In 2017, we did some field work with the USGS on the Point Sur. Kevin and I accompanied that cruise, and then we had a full-scale coring cruise on about 10 days later with LSU, University of New Orleans, and other folks on board, and it was a very exciting time. We also had collaborators from the University of Bremen coming out and Naval Research Laboratory at Stennis Space Center. So again, we focused on small areas. These grids shown here are multi-beam grids collected by the USGS on the first cruise, and the dots show the location of cores that were collected. There were also quite a few tie lines for high frequency chirp and also multi-channel seismic. And so you can see that we touched on less than about 10% of a 2,000 square kilometer study area. And so we were just focusing on these, what we call hot spots, relatively shallow water off of Southwest Pass, a deeper location of dynamic lobes off of South Pass, and then a small grid and some cores collected off of Paso Lutra. And this is the first time that all three of these sort of river outlets have been studied simultaneously since the 1970s. And it's the first time that I know of that both geology, geochronology, and geophysical data have been simultaneously collected off of these ever. So a really exciting data set. We collected multi-cores, standard ocean instruments multi-core. Our Bremen collaborator brought out up to a 10-meter long free fall cone penetrometer, and we used a standard benthos piston coring system to collect cores up to about 9 meters in length. Now, one of the coolest things that happened during this whole project was this story. During the USGS mapping effort, we relocated the wreck of a fuel tanker that was torpedoed by a German U-boat in 1942 off the mouth of the Mississippi River Delta. And we did some really cool seabed dynamics work based on that. This is Jason Chater's group. And this is a science article that was published on it. And this is a multi-beam rendering of the ship, of the SS Virginia. So the Virginia actually settled down onto a complex of mud flow lobes south of Southwest Pass. And this is a multi-beam image showing very clearly the distribution of the lobes. And then this darker blue down here in deeper water is the pro-delta. The ship was, like I said, a fuel carrier that was torpedoed in 1942, and it's now a war grave site. So the U.S. Department of Interior is very interested in maintaining the integrity of this. Also, though, the ship, the location of the ship, it's actually been moving over time. So, for example, from 2003 to 2006, it moved 370 meters. From 2006 to 2007, it moved about 65 meters downslope. And there's no apparent drag mark or deformation of the ship itself. So what we're seeing is the motion of this complex of mud flows gliding downslope over time. Now, Jason did a more in-depth time series analysis for the paper they published a couple of years ago. And essentially what we're seeing during periods of major hurricane strikes, the mud flow complex moves downslope up to about 180 meters per year, which is a lot this is a big area. During a period when there was one Cat 3 hurricane strike, about 18 meters per year. And during a period when there are no hurricanes, sort of creeping at about 1 meter per year, as best as we can tell. Now, this is not the only data set that we have for seabed motion. Jason was also able to do a time series analysis from 2016 to 2017 data sets from a US government data set in 2016, and then his own data set in 2017, looking at coherent blocks of sediment, big sort of mud boulders in these gullies, tracking their motion downslope over time. And this Rose diagram in the lower right-hand corner of this figure shows that on average, these blocks are moving to the south-southwest at rates of 5 to 25 meters per year during a period with no hurricanes. So these things, from a geological perspective, they're really cruising along. So there have been some examples of this done before. This is one of the most extensive estimates of time series motion that's been done to date. What we see here, really sort of one of my last figures, and I'll have plenty of time for questions from everybody. This is an interpreted multi-channel seismic figure that actually, this is chirp data that shows examples of uninterpreted and interpreted data with a mudflow lobe that's shown here in yellow, with amalgamated mudflow lobe layers shown here in light brown, and then pro-delta sediments that have this beautiful parallel lamination underlying that. So you can see the impacts of this of the sediment accumulating and these flows sliding down across the pro-delta. You can also see, if you look closely, there's some fault evidence for normal faulting in these, and this is characteristic of much of the delta. And these are widespread, and interestingly, these kinds of faults show surface expression in some locations, also within the vicinity of pipelines. So there's all kinds of things that you need to consider when you're thinking about placing infrastructure out in here, not just mud flow dynamics, but fault dynamics, and not just hurricanes, but also seasonal creep or sort of progressive motion of these types of deposits. So some of the major findings to date is that the subaqueous delta from Jillian's really great work, the subaqueous delta is diminishing in volume, so it's transgressing, and this is due to declining sediment load to river outlets. Land loss has been, terrestrial subaerial land loss has been recognized for decades, but ours is the first documentation of submarine changes, and this has been noted in some of the great subaqueous deltas of in the East China Sea. And I think many of the people on this call are experts in this. And so we're seeing this now the same thing in the Mississippi Delta. During periods without major hurricanes, we see a lot of evidence that most of the sort of shallow seabed dynamics is controlled mostly by hydrodynamic sediment transport. This is one of the first times where we've had closely coupled sediment sampling, geophysical data measurements, and radioisotope measurements to get a really comprehensive understanding, at least on a local scale, of morphodynamics. Major sediment transport, major mass transport in gullies and lobes does seem to be associated with detachment planes deeper than about 3 meters in the seabed. We think we see this from core results. It's kind of hard to identify in geophysical data, but it's something we need to better understand. Importantly, hurricanes are not required to drive kilometer scale mass transport. The highest rates of motion do coincide with hurricane disturbances, but the seabed is very active in all conditions. Fair weather mass transport in gullies and lobes also poses an infrastructure risk to platforms and particularly to pipelines, but it's poorly understood. And Kevin and I are supervising student work on a number of projects right now that are going to produce some more, I think, some more in-detailed and insightful geochronological results in the next couple of years. So we think a lot about this in terms of what we need to understand the risks associated with resource development off the Delta. It's a huge area. We have very limited data still. There's a lot of dynamics and great changes and no really detailed regional studies since the 1970s. And the tools that we've been able to afford to use so far really don't enable us to get a great understanding of what's going out. For example, some of these landslides, like the Hurricane Ivan Taylor platform landslide, is a slab of 30 meters in depth. And we don't have the tools, our geophysical tools can't see through the gas for the most part, at least for high frequency measurements. And the coring tools don't penetrate the depth of the slab. So it presents a real problem in terms of generating understanding. We don't know exactly when, why, how fast, or how deeply sediments move during active sliding. And very importantly, our older approaches for risk assessment from waves appear to underestimate the forces that are applied by waves on the seabed under some conditions. Importantly, the role of biogenic gas and the influence on submarine landslides is likely critical, but there have only been a handful of studies that have been conducted on this under fairly primitive conditions in the 1970s and early 80s compared to what we can do now with pressurized coring tools. So from a US hazard and resource and risk assessment perspective, there needs to be a comprehensive effort here. We thought that one of the federal agencies was going to fund this a couple of years ago. We're still looking for a funding partner for this. We would like to be able to track flows using in situ instrumentation, study gas more specifically, develop some new modeling tools that can deal with sort of the multi-phase characteristics of these flows, and essentially generate a new class of hazard maps, sort of digital layers using the Corps of Engineers and Emergency Management Agency approaches for storm and hurricane forcing. And this is really going to require a substantial expansion of research team and capabilities. We estimate a cost on the order of $20 to $40 million to fund a project like this. But when you consider that one platform has a remediation cost of $1 billion and that there are hundreds of them out there, I think it's well worth the investment. So Bureau of Ocean Energy Management funded a good portion of this. We had great collaboration with Jason Chater at the USGS and his team, with collaborators at NRL and University of Bremen. We got surveyed data from JP Walsh, from a number of other companies, including Fugro. Coastal Studies Institute provided a lot of support for this. Everyone in all of our labs contributed to this. And the LSU Harrison Endowment for Sedimentary Geology also chipped in some money for the project. So thank you very much, and I'll be glad to answer any questions. I think we got plenty of time.
Excellent, Dan. Any questions? Now we open the floor. If you have any questions, you can unmute yourself and you can ask the question directly. If you prefer to type the question in the chat box, you may also do so, and I can read the question to Sam.
Sam, great talk. And so so amazed to see the result you showed, the warship, the Virginia, you found the drifting. And that's such a great evidence to show the flow mod, the landsliding. Basically, we cannot get such a reference object. You guys so lucky, and it's so good. So my question is how you track the moving of the boat? You have to go back to survey, keep serving there, or
yeah. Each one of the time points is based on a time series bathymetric survey of some kind.
Wow.
Yeah, because there are the ship has moved, I think, 10 kilometers since you sank. And
how
so
deep? How deep the water? 200 meters?
No, it's about 80 meters right there.
80 meters. Okay.
Yeah, it's perched up on top of a mudflow lobe complex. So
I see.
It's not too deep, and it's still under the sort of the distal effects of the plume as well.
Okay.
So there's active sediment accretion too.
It's just I just have a creative idea. If we attach a wire to the boat and put a buoy on the surface, then you can get a real time checking the moving. It's a low cost way to track the mudslide.
You're exactly right. However, because it's a war grave and because we don't want people to know, it's actually within the limits of very difficult but technical diving depth. And we don't want anyone to go out and try to do any salvage operations.
Oh, gosh.
So the Bureau of Ocean Energy Management requires us to, you'll notice there weren't any coordinates on that map. We don't release the actual location of it.
I see. I understand.
All the fishermen out there know more or less where it is because they've lost nets on it.
Okay.
But we can't actually broadcast the detailed location of the ship.
I understand, but this is a very good sense. If we put a tripod there, could be moving down even far distance. In the
That's
ocean.
right, and one of the ideas that Kevin and I have explored with a lot is putting out like near the ship and like maybe in the gullies, some high frequency transponder systems where we have like a base station and a tripod mounted down in the gully, so that you can measure the relative offset, or a long range system where the base station is actually mounted on an oil platform. So Charlie Paul out at Monterey Bay Research Institute, he's done work kind of like this, and he's actually part of the team that submitted the proposal that did not get funded for the major study. But there was a lot of cool technology that went into that proposal that we're not going to let go of.
Yeah, very good. Keep on there. You will get it. Thank you very much. Fantastic. That's very good.
Any other questions? We have a large number of Chinese colleagues on this webinar. I have been reading some published papers. I know there are active submarine landslide in the Yellow River Delta front. So I believe there are a few scholars or scientists in this webinar who study the Yellow River Delta. So if you have questions, feel free to ask now.
Also, if anybody wants to strike up a collaboration on some of these data sets, I mean, Kevin and I are still working with them, and feel free to reach out to us at any point. I think our emails are in the connection information for today's call.
Any questions? Can I make a comment, Sam?
Yeah, sure. Please do, Kevin.
Yeah. Speaking of hurricanes and storms, so Hurricane Ida passed the northern Gulf of Mexico about 15 or 20 days ago, and it caused massive damage. And I hope our colleagues, friends living in the northern Gulf stay safe. And right now, Tropical Storm Nicholas is passing Baton Rouge, Louisiana. So the fact that we can still run an online virtual seminar or webinar demonstrate the resiliency of our coastal community. I mean, we can do this even during the passage of a tropical storm. So I'm so grateful about the fact that we can do this and we can utilize the modern technology.
You're absolutely right. And another, Paul and Kevin and I were talking about just before the webinar started, something that if anybody wants to follow up with communications on, I'd love to hear. Kevin mentioned Hurricane Ida that came on shore about, I guess, what, 2.5 weeks ago, Kevin?
Mm-hmm.
So Ida went from being more or less a tropical depression or a tropical storm to a Category 4 hurricane with wind speeds of what are the Cat 4 wind speeds in kilometers per hour? I can't remember, but very powerful, major storm. But it intensified in just something around 24 hours, going from a very weak state to a very powerful state. And that is very different from what we are used to dealing with in the coastal ocean. And if any of the listeners today have got sort of scientific experience with intensification and coastal impacts of storms like this in your home territories, I'd be very interested in talking to you about it, because we're going to be thinking about establishing some more international collaborations in delta dynamics and specifically, but related to human risks and hazards to humans, which of course for many of us includes tropical cyclones. So the intensification rate is problematic because in the Gulf of Mexico, it happens so quickly that we can't evacuate. And so it's a serious issue. And I'd be interested in hearing insights from for any of you who face this internationally elsewhere.
I think we get 2 questions. How about Dr. Jun Xu first, and then Dr. Islam the next?
Hi, Sam, and thank you for your great talk. And very good, very interesting. And I have just one question about, it's very interesting you have calculated the seaflow pressure. I was wondering if you have considered wind direction in your simulation or modeling sea flow pressure. And you just talked about the different hurricanes, and hurricanes have a strong effect, and also in terms of wind direction. I was wondering if you have considered wind direction in your sea flow pressure calculation.
Well, first of all, when we published this paper, it was our colleague Ioannis Georgiou who did the modeling work for this. But we used a very simple setup with a single hurricane scenario, and it's extremely limited. Exactly like you say, it doesn't really show a good a good sort of Monte Carlo type distribution of effects. But what we had proposed to do in our larger project was to do just that, use sort of a Monte Carlo approach to storm intensity, storm track, and wind direction, those sorts of things, to get a more widespread distribution in space and time of pressure differentials, just like what you're talking about. So for the geology paper, it was very much oversimplified. We recognize that, and we want to do a better job if we can get the money to go to the next level.
Thank you. Thanks.
Sure.
Yeah.
Okay,
Dr. Islam.
Dr. Islam, please.
Thank you very much for your nice presentation. It's very informative. Particularly, I come to know about what is happening in the delta front area of Mississippi River. I'm speaking from Ganges GBM area. So one thing is to know, just 2 query I need to know about. Despite this landslide, that is the landslide in the delta front area, how is the sediment reworking characteristics in the river, in the bed area? Because due to some regular oceanographic process such as tide, ocean current, this one thing. And the second question, so far I understand there are lots of human intervention in that area. Fishermen's activities, I think, and then lots of pipes and line and lots of gas explosion. How human intervention has changing the topography, bottom topography in the delta front area of your area. Thank you very much.
Those are really great questions. The first one is touching on sort of oceanographic and hydrodynamic. I mean, when I'm talking to my students, I think of I've sort of described the mechanisms for sediment transport in terms of hydrodynamic and versus gravity driven. And probably we have weak tides. It's microtidal, sort of mixed tidal system, so we don't have strong tidal flows. Probably the strongest hydrodynamic outside of hurricanes, the strongest hydrodynamic impact is winter storms, which come through about every 3 to 5 days for around 6 months out of the year. And those are pretty effective at reworking maybe the top 10, 15 centimeters at most of the seabed. And you can see the effects of that in sediment cores pretty clearly. So that is very important, and it moves sediment around and redistributes it after initial deposition. But I think in terms of, you know, the volume of sediment motion, the biggest post-depositional impact comes from various types of mud flows. With respect to human impacts, in terms of human controls on the seabed, we haven't actually looked at that in great detail. My sense is that if you consider the scale of the area, that that much of the sediment motion and much of the morphology, if you're not looking specifically at a pipeline or at a oil platform, much of the morphology remains fairly much in a condition of natural characteristics. That said, the reduction in sediment load by the Mississippi River that has been caused by humans over about the last century is having remarkable impacts on the seabed morphology. And given long enough period of time, if you cut down on the sediment load, you're also going to reduce the submarine landslide risk, because the rapid sedimentation is just going to cease. But that'll take a while, and we've got a lot of issues with seabed hazards right now. So thank you very much, sir, for your questions. Please reach out to me by email if you want to follow up anymore.
Thank you.
Hey, Kevin, may I add a quick comment?
No problem. Go ahead.
Yeah, it's a follow Islam's question. You know, Ganges Brahmaputra is one of the big river delta I can think about in terms of the landslide, submarine landslide compared to the Mississippi, but even more. So Islam, you know, we should have that channel, have a communication, say, you know, we do a comparison of that, you know, sediment sliding to the deep sea from the active sediment lobe, delta lobe. So the Ganges Brahmaputra definitely is one of them.
That's right. I mean, you have a much stronger tidal system. We probably have more seasonality in terms of winter to summer, you know, cold fronts coming through, and we both have tropical cyclones. So from a sort of a power distribution for hydrodynamics, it could be really interesting to take a look at.
Okay, any other questions?
Cool.
Well, thanks, everybody.
Thank you, Sam.
Thank you.